Welcome to Where Light Ends. Today, we're tackling something, well, fundamental, something you feel every single second. But what if it doesn't actually exist? Not in the way you think, anyway. What if time itself? What if it's an illusion?
Sounds completely counterintuitive, doesn't it? I mean, our whole lives revolve around time.
Right, but this isn't just some, philosophical thought experiment. It's a serious idea in modern physics.
Oh, absolutely. It's at the cutting edge.
So our goal today is to really unpack the science behind this pretty radical idea. We want to look at the evidence, explore some surprising ways this affects your technology.
Yeah, the everyday stuff.
Exactly, and maybe touch on those really big philosophical questions it opens up.
Definitely. And the first hurdle, it's always our own intuition, isn't it? It just screams that time is real.
Of course. We have clocks, phones, calendars. We feel it passing. Seems obvious.
It does. It seems to work perfectly fine for us day to day. But here's the twist. Time, as we usually picture it, this sort of universal river flowing everywhere at the exact same rate, that's probably more of a human perception. Maybe even a social construct.
A human perception, a social construct, like money, maybe? Or like the flat earth idea?
Yeah, the flat earth analogy is actually pretty good. Locally, if you're just walking around your city, playing football, whatever, the earth seems flat.
Sure, it works on that scale.
Exactly. And time is kind of similar. At our everyday speeds, our human scales, it seems to flow nice and steady. Our watches, even really good ones, they may be precise down to milliseconds.
Right, good enough for us.
Good enough for us. But the effects showing time isn't quite what we think. They happen way, way down at the nanosecond scale, or even picoseconds. That's a billionth, or even a trillionth of a second.
Wow.
Our senses, our normal clocks, they just aren't sensitive enough to pick that up.
So we're like the flat earthers of time, in a sense, living on our local patch.
Sort of, yeah. And that gap, that space between our everyday feeling and what the physics tells us, that's where things get really interesting.
Okay, so let's dive into that then. If our intuition is basically wrong, how do scientists know? What are these super precise clocks, these atomic clocks? What are they actually showing?
Right. Atomic clocks are absolutely the key here. They are just astonishingly precise. I mean, we're talking the best ones might lose less than a second over the entire age of the universe.
13 billion years. Less than a second. That's hard to even imagine.
It really is. And because they're that precise, they demonstrate time's non-existence. Or maybe more accurately, the non-existence of a universal time. They do this by desynchronizing.
Desynchronizing, you mean they start ticking at different rates, even if they start perfectly together.
Exactly that. If time was this absolute universal thing, like Newton thought, once you synchronize two perfect clocks, they should stay synchronized forever, no matter what. But they don't. They absolutely do not. You put one on a mountain and one down at sea level, or you fly one in a fast plane, and they will measurably drift apart. Their rates change.
Oh, okay. So that drift, that desynchronization, that tiny difference, that's the proof.
Oh, it's definitely the proof.
Yeah.
But it's more than that now. It's actually a tool. It's built into technology you probably use every single day. Think about GPS.
My phone navigator, how does that rely on time? Weird.
Well, yeah. Those satellites whizzing around Earth, they're moving really fast, maybe 14,000 kilometers an hour.
Okay.
And they're further out from Earth, so gravity is slightly weaker for them up there.
Yeah.
Both those things, speed and gravity, affect time, according to Einstein.
Right, relativity.
Exactly. Now, if the engineers just assumed time was the same up there as down here, that the satellite clocks ticked at the exact same rate as clocks on Earth, well, your GPS position, it would drift off by about 22 kilometers. Every single day.
22 kilometers, that would be completely useless. I'd end up in the wrong city.
Utterly useless. So the very fact that your GPS works, that it can pinpoint you down to, a few meters, that's direct, everyday proof that there's no single universal time.
Yeah.
Engineers have to constantly correct for this desynchronization, this difference in clock rates predicted by relativity. It's built into the system.
So my phone navigating relies on time not being absolute. That's actually amazing. Are there other examples like that?
Oh, definitely. You can actually use atomic clocks as incredibly precise altimeters, like measuring altitude differences down to centimeters.
How? Just by comparing clocks?
Yeah, because gravity affects the rate of clocks. Remember, a clock just, say, a meter higher experiences slightly less gravity, therefore ticks ever so slightly faster.
A meter. So a clock on the floor ticks slower than one on the table. Seriously.
Imperceptibly to us, of course. But yes, fundamentally yes. Atomic clocks can perceive that tiny difference, measure that difference in ticking rate between two clocks, and you can calculate the height difference between them.
Wow.
If time were universal, that just wouldn't work at all.
That's wild. Any other uses? That feels like sci-fi.
Well, it even extends into things like geology, because clocks are sensitive to gravity, and gravity changes slightly depending on what's underground.
Ah, like if there's dense rock or maybe water or oil.
Exactly that. So you can potentially use arrays of these super-sensitive clocks to map out gravitational variations and detect hidden resources. So yeah, what started as Einstein's pretty radical insight over 100 years ago is now a practical tool. It's just part of modern physics and tech now.
Which brings us back to Einstein. I mean, how on earth did he figure this stuff out way back then? Without atomic clocks, without GPS flying around, what was he seeing?
Well, it's key to understand he didn't just, dream it up in isolation. He was building on existing work, analyzing experiments that didn't quite make sense under the old rules, and using these brilliant thought experiments.
Like what kind of problems was he thinking about?
He started thinking about a very practical problem they had back then. Synchronizing clocks over long distances, for things like train schedules between, say, Paris and Berlin.
Okay, yeah, coordinating things across distances. Makes sense.
But the problem is, how do you synchronize them accurately? Any signal you send, whether it's light or radio waves, whatever it takes time to travel, you can't instantly know what time it is somewhere else.
Right. The speed of light limit. Nothing's instantaneous.
Precisely. And really thinking through the implications of that led him to this revolutionary idea. Simultaneity itself must be relative.
Meaning
what one person sees as happening at the exact same time might not be simultaneous for someone else, especially if they're moving relative to each other or if they're very far apart.
So now isn't the same now for everyone everywhere.
That's the core of it. The idea of a universal present moment, a single now across the cosmos, it just doesn't hold up physically once you account for the finite speed of light. And actually, there was experimental evidence pointing this way already. The Michelson-Morley experiment, way back in the mid-1800s.
Yes, I've heard of that one. It was trying to detect the ether, wasn't it?
Exactly. And it famously failed to detect it. But what it did show was that the speed of light is constant, no matter how the source or the observer moves. This completely baffled physicists. It clashed directly with Newton's ideas of absolute space and time. They were stuck on this for like half a century.
Why? What was the sticking point?
Because they couldn't bring themselves to question the existence of absolute time. It seemed too fundamental. It took Einstein in 1905 with his paper on special relativity to basically say, look, the experiment is right. The speed of light is constant. It's our cherished idea of absolute time that's wrong. We have to ditch it.
That was a bold move, to just throw out absolute time.
Incredibly bold.
Yeah.
So physics fundamentally shifted. We stopped talking so much about time as this universal thing and started talking about duration, or more technically, proper duration. Clocks, he realized, don't measure some universal river called time. They measure the duration of their own path, their own history, through whatever it is.
So a second isn't a unit of universal time. It's a unit of duration experienced along a path.
Exactly. Just like a meter is a unit of length along a path in space. And then Hermann Minkowski, who was actually one of Einstein's old professors, he took it a step further. He realized we needed a whole new framework. Not space and time as separate things, but space-time.
Space-time, this single, unified, four-dimensional fabric weaving together the three dimensions of space and this dimension of duration.
That's the picture, yes, a unified geometry.
Okay, space-time. So if time isn't flowing in that old sense, what are we doing? What's happening to us right now, second by second, in this space-time picture?
Well, in this space-time framework, everything that exists, every object, every person, every particle traces out a path. It's called a world line.
A world line.
Yeah. Your world line is the unique trajectory you follow through space-time from your birth to your death. It's essentially a sequence of events, your history plotted in 4 dimensions.
Like a line drawn on this space-time fabric, mapping out my entire existence.
Kind of. Yes, that's a way to visualize it. And the duration you experience, your age, how long you live, is essentially the length of your specific world line, measured according to the geometry of space-time.
The length of the line determines my experience duration. Okay. how does that then explain weird things like the twin paradox? You know, the one where the twin who travels in a spaceship ages less.
Ah, the Langevin twins paradox, yes.
Yeah.
It's a perfect illustration of this. The twin who travels at very high speed in a spaceship and then returns. Their world line, if you calculate its length in space-time geometry, is actually shorter than the world line of the twin who stayed on Earth.
Shorter, even though they went on a long journey. That seems counterintuitive.
It is.
Uh-huh.
But it's because of the way speed and also gravity and general relativity warp space-time. High speeds effectively make your path through space-time shorter in terms of proper duration. So the traveling twin literally experienced less duration. They aged less.
Their heart beat normally. They live normally from their perspective.
Totally normally from their perspective.
Yeah.
But the total length of their journey through space-time was less.
So different paths through space-time mean different total amounts of aging, different durations.
Precisely. Each clock, each person, each object measures its own proper duration along its own unique world line. There's no universal clock overseeing it all.
That makes a strange kind of sense now.
Yeah.
But here's the really big question for me. If my world line is just this sort of static path in space-time, containing all the events of my life, past, present, and future laid out, why do I only remember the past part of it? Why don't I remember the future events on my world line? And why do I experience it sequentially, like tick-tock, second by second, instead of just perceiving the whole thing at once?
Yeah, that is the million-dollar question, or maybe the trillion-dollar question. And physics, quite honestly, has no definitive answer for that why.
Really? No idea at all. After figuring out space-time and relativity...
Not really, no. We can describe the world line, the space-time geometry, the sequence of events, the different durations, but why we perceive a flow, why there's this psychological arrow of time, past, remembered, future unknown, experienced sequentially, that's a profound mystery. It might have something to do with thermodynamics, the increase of entropy. Maybe it's related to the initial conditions of the universe. Maybe it's even connected to consciousness itself. But it's not something explained directly by relativity or quantum mechanics as we currently understand them.
So physics gives us the map, the space-time structure, but not why we experience the journey along that map in only one direction, moment by moment.
That's a very good way to put it, yes. And this whole space-time idea with everything kind of lit out, it opens up even weirder possibilities, doesn't it? Like time travel.
Yeah.
Or what physicists call closed time-like curves.
You mean looping back on your own world line, ending up where you started, but earlier?
Exactly. Paths through space-time that could theoretically lead back to an earlier point in time. Stuff of science fiction. But Kurt Gödel, Einstein's friend and colleague at Princeton, a brilliant mathematician, he actually found solutions to Einstein's own equations for general relativity back in the 1930s that seemed to allow for this kind of thing. Universes where closed time-like curves could exist.
Gödel found potential time travel loops in Einstein's math.
Mathematically, yes. Apparently, it made Einstein quite uncomfortable. Later on, people like Stephen Hawking proposed maybe there's something like a chronological protection conjecture that the laws of physics somehow conspire to prevent these paradoxes from actually happening in reality.
Like the grandfather paradox, right? If you could go back and, prevent your own grandparents from ever meeting.
What physics seems to suggest, if such travel were possible, is a kind of principle of coherence. If you could travel back, the laws of physics would essentially force things to happen in a way that avoids a paradox. Your free will would be constrained to ensure that what happened still happened.
So you couldn't actually change the past even if you went there? It's fixed. It just is.
In this space-time block universe view, yes, that's the implication. It's almost like that old myth of Oedipus: the more he tried to avoid his prophesied fate, the more his actions led him right to it. If an event is part of your past world line, it exists in space-time. Traveling back wouldn't erase it. You'd just be fulfilling your role in it, perhaps.
Wow. Okay. This exploration here on Where Light Ends has certainly bent my brain around the idea of time. So just to sum up, what feels like this universal flow, this time we all share and measure, is maybe more like a personal journey. Right. Our own duration ticking away along our unique world line in this grand fabric called space-time.
That's a pretty good way to think about it, I think. Not a single river we're all floating down, but countless individual paths.
And understanding this isn't just some abstract theory for physicists, it's actually essential for technology we rely on constantly, like GPS, like those super precise altimeters, maybe even finding things hidden underground.
Absolutely. It's fundamentally baked into modern science and engineering now. We have to account for it.
So here's maybe a final thought for you listening. If all events, past, present, future, just are laid out in this space-time structure, and our feeling of now is just us moving along our predetermined world line, what really makes yesterday's memory different from tomorrow's possibility is that feeling of flow, that passage of time, just a trick of our minds perhaps, hiding a reality that's, well, already complete. What might you find out next on your own world line? Thank you for following us on Where Light Ends. Don't forget to subscribe.